Is everybody there? Can I start now?
Sure.
Hello.
Okay, great. Uh, First of all, let me share my screen. Okay, can everybody see the first slide of the PowerPoint file?
Yes.
Okay, parallel resonance is written. Okay, so before starting, just a couple of the things. Today, a while ago, I sent you an email stating that I have uploaded the homework set 4. Did you receive my email?
I saw it right before class.
Yeah, sure did.
Yeah.
Okay, so I uploaded the homework set 4 on eCourseware, and I created a Dropbox titled homework set 4. Can you see that Dropbox?
Yeah.
Yeah, it's a
Yeah, I mean, you need to click on eCourseware page on the assessment, and then you will see there are a couple of options there. You have to click the Dropbox, then you can see that one.
Yeah, I
And
see it.
then, yeah, okay. And homework 4 I uploaded as usual on that homework tab on the eCourseware. So what you have to do, you all need to solve those problems. There are 5 problems on homework set 4, and then you will be uploading. You will be scanning and then uploading those files on the Dropbox titled homework set 4. And the due date is on coming Monday, March 30. You can submit until midnight. I think I have set up time until 11:30 p.m. And in the email, I also mentioned that regarding lab report submission, you all remember that you did experiment 4 just before the start of the break.
Right.
That is lab 4. So I have created a tab titled report for experiment 4 on the lab sections. That is not on the usual class, on the lab sections. And I set up the deadline to submit that report by this Friday.
All right.
So is everybody fine?
I can see it
Thank you.
now.
Yep.
Thank you.
Can see it.
Yes.
Could you see that Dropbox on the lab sections, not on the
Yes,
class
I
page?
see it.
Yeah.
Okay, great. Okay. So therefore today, you know, that lab TA Mahfouz will be joining with you, perhaps at the scheduled time. And he will be discussing about experiment 5 and then design number 2. I mean, labs together. Design number 2 and lab number 5. And I already uploaded those material YouTube link on the eCourseware. Have you seen those? I mean, for lab number 5, I think there are 3 YouTube links that I uploaded on the lab sections only, not on the class page.
Yeah,
Okay, and then I uploaded on a Word file, including all the measurements that Mahfouz has taken for it. This means you all need first understand those YouTubes, his explanation, circuit diagram connections, and then you need to look that Word file, including those measurements or readings. And based on those, you have to prepare the lab report. So I will create another Dropbox for you for that. That is due probably next week. Still, I did not set up the deadline. And
Yeah.
today, the lab due will instruct you something. So is everybody fine?
Yep.
Yep.
We're
Okay.
good.
Okay. So then now moving forward, let's have a look at parallel resonance and slide number 1. So as you can remember that in last class we were discussing series resonance with regard to that series RLC circuit. And today we will be discussing parallel resonance with regard to that parallel RLC circuit. So as you can see in the circuit, there is a current source with magnitude Im and phase angle theta. That current source is powering those three branches R, L, and C. And then the bottom figure is the phasor domain circuit or phasor equivalent circuit. As you can see that for L it is j omega L, for C it is 1 over j omega C. Now based on that parallel circuit, we will be looking at how that resonance occurs. So therefore now I am going to slide number 2. As you can see in this slide, on the top, I have written H omega. H omega is the transfer function for that circuit. Basically, that is the admittance. You see, I have written Y. Y is the admittance, reciprocal of that impedance. So admittance is 1 over R plus 1 over j omega L plus j omega C. And you see, I have written 1 over L plus j in parenthesis omega C minus 1 over omega L. So now that's the expression for the admittance. Now the condition for the parallel resonance is that the imaginary part of that admittance or transfer function should be 0. That's why what I did, I have written omega C minus 1 over omega L equal to 0. And that finally gives me omega naught 1 over root over LC. So everybody understands so far?
Yes, so far.
Yeah. So in the Y equation, just look the imaginary part. So I am equating that imaginary part to be 0. That gave me omega naught 1 over root over LC. Okay, so moving forward, you see the last equation in this slide, magnitude of V voltage for that circuit shown in the previous slide, Im over root over 1 over R squared plus omega C minus 1 over omega L squared. So that is the magnitude of the voltage. Now, using this voltage expression, we will construct that voltage versus frequency or that angular frequency omega curves. So let's have a look in the next slide. But keep in mind this equation. Okay, so see this on voltage amplitude versus the frequency for the parallel resonance circuit. So you can see likewise the series resonance case. Here also there are 3 points on the omega axis. One is omega naught, which is the resonance point. And then there are 2 points, omega 1 and omega 2, which are called half power frequencies. So as you can see on the y-axis, that is magnitude of voltage axis, corresponds to omega naught. Magnitude of voltage is Im multiplied by R. So this means, I am going back to the previous slide once again. If you see the last equation for voltage magnitude, because the condition is omega C should be equal to 1 over omega L, so that term vanishes. So in the denominator, you are getting after root square 1 over R, and that R is going in the numerator. So that makes Im multiplied by R. So that's why on the characteristics curve, you are looking the voltage magnitude Im multiplied by R corresponds to point omega naught. And the 2 half power frequency points, that is omega 1 and omega 2, as you can see, the voltage magnitude is Im multiplied by R over root 2. So as you know, by the definition, Happer frequency means where the value is 0.707 of the peak value. That means of the Im multiplied by R. So that's how you can see it is divided by root 2. So is everybody fine on this slide?
Yeah.
Yeah.
That's good.
Okay, great. So now moving forward, actually the goal is likewise the series resonance. You have to find out those two Happer frequency points, that is omega 1 and omega 2. There will be two long expressions that I will be showing you. So moving forward, in this slide, before going to that calculation, everybody see I have written for you average power dissipated by the RLC parallel circuit is P omega, means that resonance point have V squared multiplied by G. So you remember that G means conductance. Because this is parallel circuit, that's why it is multiplied by G. So this means V square over R. And the highest power dissipated at resonance, P omega naught have, and then because at resonance point that you noticed in the previous slide on the characteristics cards, V equals to Im multiplied by R. So Im multiplied by R squared. And then in the denominator it is R. So finally you are getting half Im squared and then R. If in the numerator it is R squared and in the denominator it is R. So on R is getting cancelled. So on the same fashion, the power at frequency omega 1 and omega 2, P omega 1 equal to P omega 2 have, and look the numerator, Im R over root 2 and then whole squared, because that is the half power point that you noticed in the characteristics card, and then whole divide by R. And finally it is making 1 by 4 Im squared R. Now if you compare the power at omega naught, this means the second equation, and then the third equation, power at omega 1 and omega 2, power at omega 1 and omega 2 is half. That's why you can see 1 by 4. And that makes sense. And that is the reason those 2 points, omega 1 and omega 2, are called the half power frequency. Is everybody fine so far?
Yeah, looks great.
Okay, fine. So moving forward in the next slide, now our target is to calculate those 2 points, omega 1 and omega 2. So as you can see, Vm at omega 1 and omega 2 is Im multiplied by R over root 2. This means Im over root 2 over R. As you can see, it is the same meaning, but I'm writing in that way to show that root 2 over R, that is the admittance. Now, if you see what I have written, the half power frequencies can be obtained by setting y equal to root 2 by R. So see the equation, left side, all root over 1 over R squared plus omega c minus 1 over omega u whole squared equal to root 2 over R. And then see the next line, I made squared on both sides to omit that squared sign. So finally, you are getting the second equation from the bottom, omega c minus omega 1 over omega L squared minus 1 over R squared. So this means this corresponds to that basic algebra equation a square minus b square, which is like a plus b into a minus b. Therefore, look the very last line, which is omega c minus 1 over omega L plus 1 over R, which is equivalent to a plus b. And then in parentheses, omega c minus 1 over omega L minus 1 over R equal to 0. So this is equivalent to A minus B. So now, based on that, this is the equation. As you can easily guess, there will be two solutions for omega based on the left side component and then the right side component in parentheses. So moving forward, see this slide. First look the left side, omega c minus 1 over omega L plus 1 over R equal to 0. And then I'm simplifying, and you see the third line on the left side that is actually a quadratic equation. Omega squared plus omega over C minus 1 over LC. So now, because this is quadratic equation, so see the fourth line, I have written down the solution for that quadratic equation. Like you remember, x squared plus bx plus c equal to 0. Then x should be minus b plus minus root over b squared minus 4ac over 2a. So exactly I have used that identity that you all know. And then in the fifth line, I have written combinedly omega 1, 2, because there would be two solutions. And then finally, we are getting the last two expression, omega 1 and omega 2. But you see what I have written that here omega 2 is negative. So it can't be a solution. So this means everybody see on the left side, last two expression, omega 1 is minus 1 over 2 RC plus root over. So therefore this should be positive. But the very last one, omega 2, because there are minus sign on both terms, so it's always negative, and it can be a solution. Because what we are looking for those two half power points which are omega 1 and omega 2 on that characteristics curve. And as you can remember that curve, both are greater than 0. So definitely both should be positive. Now if you see the right side, another term at the first line, omega c minus 1 over omega L plus 1 over R equal to 0. Sorry, minus 1 over R equal to 0. And then likewise the left side, I am simplifying and moving, and then see the third line. This forms another quadratic equation because there is omega squared. So the fourth line is the solution. Then fifth line is combined solution for omega 1, omega 2. Finally, the last two expression, one for omega 1, the other for omega 2. So in this case, you see I have written here omega 2 is negative. So it can't be a solution because you see omega 2 has negative. First term is positive, but second term is negative. But second term definitely will be greater than the first term, so that will be negative. So that can't be a solution. That's why omega 1, you see the whole thing is positive. Now, if you compare this omega 1 on the right side, and if you look the omega 1 on the left side, on the right side, this omega 1 must be greater than the left side omega 1. This means you can conclude that right side omega 1 is actually omega 2 and left side omega 1 is omega 1 on that plot. So therefore, in the next slide, I have concluded the final solution for the omega is omega 1 minus 1 over 2 RC plus that term, and then omega 2 is plus 1 over 2 RC plus this one. Everybody, could you follow me what I told?
Yeah, makes perfect sense.
Yes, and that makes sense. You know that similarly, actually we did on Monday's class for the series resonance. Exactly similarly, we are doing everything the same, only difference. Today we are discussing the parallel resonance. Okay, then moving forward in this slide, as you can see, I am saying quality factor Q. As you can remember in the last class, we also discussed the same thing, quality factor, and then definition of the quality factor was that how much reactive energy was produced in L and C with respect to how much energy is consumed by the resistance. The same definition goes for parallel resonance. Therefore, if you see the expression of QL, V square BL multiplied by T, you see here it is multiplied by BL. BL means inductive susceptance. You remember in case of series resonance, we multiplied by XL, that is the inductive reactance. But because today we are looking into parallel resonance, that's why we are multiplying by BL. So you remember this symbol stands for susceptance for parallel circuit. And BL is because we are looking at quality factor for inductive circuit. And then multiplied by T, which is the time period overall cycle of that waveform. So then reactive power in inductor multiplied by the time, that is making the reactive energy. And then if you see the denominator, V square G, this means that is the power consumption or power dissipation across the resistance. And once you multiply it by T, then that becomes energy. So now if you see the numerator, denominator, T cancelled, V square gets cancelled. So in the numerator, BL means 1 over XL. You know that susceptance is the reciprocal of reactance. Similarly, the denominator, G becomes 1 over R. The G is the conductance and R is the resistance. Conductance is the reciprocal of resistance. So then, and you know that in the numerator, XL is omega L. So that's why finally R over omega naught L. And we put omega naught to show the resonance case. So if you remember the series resonance case, the quality factor QL has different expression, but in this case, it's different. So this means in the homework or in exam or anywhere in FE exam, if you are asked to calculate the quality factor, if it is for series circuit, then one type of expression. If it is for parallel circuit, then different expression. That you have to take care and look carefully. So similarly, the next expression, QC, this means quality factor with regard to capacitor. And then same way, A square BC, capacitive susceptance multiplied by time, that makes the reactive energy over V square GT. And then TT get cancelled, V square cancelled, and then in the numerator 1 over XC, denominator 1 over I. But you all know XC is 1 over omega C. That's why ultimately omega C, it goes on the numerator and it forms omega naught RC. So if you see that expression for QC, omega naught RC. So therefore in the third line you see finally I'm concluding Q equal to R over omega naught L equal to omega naught RC. So here is on catch point. Everybody, please listen to me carefully. In case of the series circuit or parallel circuit, if you are asked to calculate the quality factor, then you could choose either of the equation. For example, in case of parallel resonance, you might choose Q equal to R over omega naught L, or you might choose Q equal to omega naught CR. You would get the same result. Everybody, could you follow me?
Yeah, it's great.
Yeah.
Yes.
Okay, yeah. And then, as I said, already said that I have set up homework set 4. If you see the homework set 4, I think now I believe you all are able to solve. There are 5 problems on homework set 4. with regard to series resonance, parallel resonance, and something about low pass filter, high pass filter, band pass filter, and band stop or notch filter that we discussed just before the start of the play. So just you need to look these slides, understand these equations, and then attempt those homework problems. So therefore, the last line, I'm writing omega naught root over omega 1 and omega 2, which is 1 over root over LCM. In other words, if you see those two solutions for omega 1, omega 2 on the first two expression, and then if you multiply those and then take their square root, you would get 1 over root over LCM, and that makes sense. Okay, so moving forward, here the bandwidth. So bandwidth V equals to omega 2 minus omega 1. This means in the previous slides, we noticed those two long expressions for omega 1 omega 2. If you subtract omega 1 from omega 2, that would give you 1 over RC. So this means in case of the parallel resonance circuit, you will be using this equation to find out bandwidth V. And then next line I'm writing Q equal to omega naught RC, and then Q over C are equal to omega naught. And because bandwidth on the first line B equal to 1 over RC, I'm substituting B for 1 over RC. That gives me Q equal to omega naught. And finally, Q equal to omega naught over B. Okay, and then this is the another catch point. Everybody see, I have written for high quality circuit. So you remember in last class, I was telling high quality circuit means when the value of Q is greater than or equal to 10. So if the Q value is greater than or equal to 10, that means that it is high. So the bandwidth V will be very narrow. There will be huge sharpness in the characteristics curve. So you can approximate omega 1 approximately omega naught minus V over 2 and omega 2 approximately omega naught plus V by 2. So same way, if you first can calculate Q, and if you notice the value is at least 10 or greater than 10, then directly you can use these two expressions for omega 1 and omega 2. Otherwise, you could use those two long expressions. Okay, so moving forward, in the next slide, as you can see, I will be discussing two numerical problems, and then we will be done for today. As you can see, I have already posted the solution to the following problem. This means my handwritten document in PDF file right after class lecture 20 on EcoShare. So you can see this numerical problem, this slide, and in the next slide, there is another problem. We will be discussing those two problems. I already uploaded the solution. This means today this is class lecture 20. I already uploaded that. And right after this class lecture, you will be noticing that there is a PDF file that is my handwritten document. It is already there. And here I have written down the solution, the answers. So everybody read the statement. The statement says, in the parallel RLC circuit of the following figure, let R equal to 8 kilo ohm, L equal to 0.2 millihenry, and C equal to 8 microfarad. Those values are given, and this is a parallel circuit. Now the questions are A, calculate omega naught, Q, and B, question number B, find out omega 1 and omega 2, and question number C, determine the power dissipated at omega naught, omega 1, and omega 2. So therefore, now I am opening that PDF file. Everybody see. Hello guys, can you see the PDF file now?
Yes.
Okay, great. So once again, you see, that is, I mean, you need not to be worried about the number. Like I have written example 14.8. Like I use this slide for the previous classes. Accordingly, I have put those numbers. So you need not to worry those numbers, neglect those numbers. You just read the problem statement. So you see, I'm scrolling down. First of all, you see, I'm calculating omega naught. Omega naught is 1 over root over LC. I am just substituting the values of L and C uh, from the given statement, and that gives me values 25 kiloradian per second. And next I am calculating Q. Q equal to R over omega naught L. And then I'm substituting the values of R and then omega naught just to calculate it previously, and then value of L. And that gives me Q value 1600. And next I'm calculating bandwidth V equal to omega naught over Q. So and that gives me 15.625 radian per second. And next I'm calculating V omega 1 equal to minus 1 over 2 RC plus that one. I am using that long expression that we derived today. And after plugging in all the numbers for R, L, and C, the value is 24,992 radian per second. And similarly, for omega 2, using that long expression that gave me 25,008 radian per second. And question number C, the power dissipation calculation at omega naught and omega 1, omega 2. You see, power dissipated at omega naught equal to P omega naught equal to half Vm square over R. So the Vm value was given. I am going upward. If you see the voltage expression, 10 sine of omega t. So where 10 is the magnitude of that voltage, that's why you see for the Vm here I have put 10 square, and then R is that 8 kilo. That gives me 6.25 milliwatt. This is not megawatt, milliwatt. And then power dissipated at omega 1, omega 2 equal to P omega 1 equal to P omega 2. We already know that power dissipation at omega 1 and omega 2 is half of that previous power. That's why I'm writing 1 over 4 Vm square over R. So, and then finally after plugging in Vm and R value, I'm getting 3.125 milliwatt. You see exactly this number is half of the previous power value, 6.25. Is everybody fine?
Yeah, looks good.
Everything's
Okay.
good.
Okay, great. Now, now I am going to that PowerPoint file once again. The last slide of the PowerPoint file, there is another problem. Can you see the PowerPoint file now?
Yep.
Okay. So in this case, again, I have posted the solution, I mean, together in one PDF file, this problem and the previous problem on eCourseHead. So what's the question? Look, the very first line. Determine the resonant frequency of the following circuit. So this is a circuit, you know, it's a parallel circuit. The last branch is combination of series of 2 Henry inductor and 2 ohm resistor. And then capacitor value is 0.1 farad, resistance value is 10 ohm. So for this circuit, calculate the value of resonant frequency. This means this is the parallel resonant circuit. Find out the omega naught. So now I am going to that PDF file again. This is the PDF file. So this is that problem, resonant frequency. So everybody please look carefully. I have set up one homework problem very similar to this one. So if you now understand here, then you will be fine in the homework. Everybody see what I did? I did input admittance. This means I am calculating Y. So look the first term, I have written j omega 0.1. Now look the circuit, because the capacitor value is 0.1 farad, and I am writing the Y admittance. So for capacitance, it is 1 over j omega c. That's why it is j omega c. So j omega and then c value. And then the next term, because it was 10 ohm registered in the circuit, and I have to do the conductance, that's why this is 1 over 10. And the last term, 1 over 2, 2 is the resistance value, and j omega 2 is the reactance value. Everybody is fine on the first line of the expression admittance?
Everything's good so far.
Okay, very good. So then see the next line, just next is the calculation. 0.1. First I have written the middle term. So like 1 over 10, if you see the first line, it was 1 over 10. So from 1 over 10, I have written 0.1. And then the middle term is from the first term, j omega 0.1. And the third term, what I did, you see in the first line, in the third term, for the denominator, there is 2 plus j omega 2. In order to eliminate the j sign, I have multiplied both numerator and denominator by 2 minus j omega 2. That's why you look at the denominator, it became 2 squared plus 4 omega squared. And the numerator becomes 2 minus j omega 2. Could you follow me, everybody?
Yes.
What I did, I multiplied for the third term, I multiplied both numerator and denominator by 2 minus j omega 2. So that from the denominator, j gets cancelled. Because I am multiplying by j minus j omega 2, that's why j square, and j square becomes minus 1. Then ultimately it became plus. That's why you can write plus 4 omega square. Okay, then moving forward, you see the third line. What I did, still it is third line, still it is the same. Oh no, in the third line, what I did, if you look the third term, if you look the numerator and denominator, 2 is the common factor. That's why 2 from the numerator I am getting 1 minus j omega, and then the denominator 1, 2 cancelled, so that's why 2 plus 2 omega is that. And then in the last line, what I am doing, I am separating out the real and reactive component. I am separating out real and reactive component. That's why if you see the third line, it was 0.1, so that 0.10 came, and then from the third term, there is 1 over 2 plus 2 omega squared, that came. And then the rest of the term with the j. This means from the middle term, j omega 0.1, and taking j as the common factor, so omega 0.1, and then minus omega over 2 plus 2 omega squared. Could you understand the last expression, what I did? I just separated out real and reactive.
Yeah.
Okay. And why I did that, why I am applying that technique, you see, I have written at resonance, imaginary part of y should be 0. I mean, that is our main statement today, that we are looking today for parallel resonance, that imaginary part should be 0. So that's, you see, the imaginary part means omega 0.1 minus omega over 2 plus 2 omega squared. I am making that equal to 0. Then in the expression, you see, I have substituted omega by omega naught, because this is the resonance condition. From the resonance condition, your goal is just to find out the omega naught. So finally we got the last line, omega naught 2 radian per second. So just look the calculation after the second line. Just simple. I am applying simple algebra. Omega naught 0.2. I am multiplying omega naught 0.1 by 2 plus 2 omega naught square. And finally, after calculations, I am getting omega naught 2 radian per second. Is everybody fine?
Yeah, looks great.
Yep.
Yeah.
Everything's
What
good.
Okay, what I would recommend you, because you are at home, so after the class, again, you open the slides, take a pen and paper, and then make some practice, then you will be fully fine. And then if you have any questions or comments, then you are most welcome to send me email anytime. Also, excuse me, so although in last class I told that I will be at school couple of hours, but actually today I didn't go because of the much more restriction from the mayor. So today basically I am joining from home. I might go to school, but that will be very short time, maybe 30 minutes or 1 hour only. So you have better email me if you have any questions, comments, or anything.
Okay.
Okay, so that's all for today. Now I am stop sharing, so I'm going back. Okay. So can you see me now?
Yep.
Okay. Okay. Did anybody make recording for the last class?
Make a recording. I did not. I was going to, but I need to from now on.
Oh, okay, okay. Today I am making recording. So after the class, I will be looking how does it go, and then I will be uploading and I will be sharing with you.
Awesome.
All right.
Thank you.
All right. Sounds good.
Okay. So thank you so much for joining. So then see you on Friday. And everybody, please look the Dropbox that I created for homework set 4 as well as for the lab reports. And
Will do.
today, everybody, please join at the lab day, Mahfouz's class, probably from 5:30, right? Today.
So it
please-
does start at 5:30.
Yeah.
Okay.
I think it was 5:30 today, right? And then tomorrow probably 2:30.
Yeah, tomorrow's
And
Tuesday.
it is exactly following the actual class, what was originally scheduled. Otherwise, it will be a problem. So, and you see the lab sections, I already uploaded 3 YouTube videos for that is experiment 5. And yesterday I uploaded another, I think, another video, and then on odd file, giving all the instructions how to take measurement. That is for the design too. And then Latier, he is gradually making other YouTubes or videos, and hopefully in a day or two he will be sharing me, and then immediately I will be uploading those for you, so you can see everything.
All right, sounds good.
Okay, so with that, so bye for today. So see you on Friday.
Thank
See
you,
you on
Dr. Ali.
Friday. Thank you.
Okay.
Thanks, sir. Have a good day.
Okay. Okay. Bye.